Okay, the chi-square test, both in the slides and in the book, and I said it a couple of times, but I'm going to reiterate, the most common mistake that will lead you to miss points on the chi-square test is entering the margins of the table as part of the matrix in your calculator. Right? So do not enter the totals. Don't enter total row or column into your matrix. Right? As long as you don't do that, then it's pretty straightforward when you use the calculator. Okay? It's going to compute that complicated test statistic and compute the degrees of freedom and compute the p-value and do all those things with you, or for you. Okay?
Have you sent the email about the circle value?
Yes. By the way, thank you for bringing that up. I could not remove any questions about critical values. So in order to get through the Hawks system, you're going to have to enter the critical value. So what I did two things. I limited the size of the tables so that you only had, there's 3 questions, but 2 of them have the same size table, so they'll have the same degrees of freedom. But then I also went to a lot of trouble to create that PDF file for you, and I emailed it to you, and I posted it on D2L and all that. And then this morning in class, somebody said, you know, there's a button that says show tables, and it pops up that same exact table, and it's really easy to use. Okay. So, use that instead of the one I emailed to you. I'm still proud of that, though. There you go. All right, and in the one that I emailed you, I did circle the ones you're going to use, and it's a choice of like 8 of them or something, and it depends on what alpha level they happen to give you. But I indicated on there, these are the alpha levels. They call it right tail probability, but that's alpha. Okay? So you can use whichever of those you prefer, but that should get you through the critical value. We don't do tests, hypothesis tests in here using critical values and rejection regions. We just do it with a p-value, right? So you should be okay, but you will have to enter that. And I have not had time yet to check on the new homework set for today to see if it does the same kind of thing where you have to know. You have to enter a critical value. Hopefully not. Okay, so let's go ahead and go to the new section, which is chapter 11. So another day, another chapter. Seems like we're just really blasting through these things now, doesn't it? So remember that series of questions that I make you ask? Is this a means problem or a proportions problem? Oh, means. 2 population means. Is it 1 sample or 2? 2. Now it doesn't say on here, are they independent samples or are they dependent samples? These are independent samples in section 11.2. We'll do dependent samples in another section. Right? So that's still to come. But what we'll do today requires independent samples. Okay, so like all inference procedures that we've been dealing with lately, there's a set of assumptions that have to be met. And this is part of going through the process of figuring out, well, which one am I supposed to be using here? Right? So if it's a means problem, 2 populations, sigma is unknown, and we aren't going to do the sigma known case, by the way, for hypothesis testing. We did that a long time ago. We're done with that. So here are the assumptions. Notice that these are identical to the assumptions you had when we did confidence intervals for difference in 2 means. Right? So it's just another way to do inference, exactly like the confidence interval one. So everything that we did then is still going to apply now. So samples have to be random. Right? Random samples. That's always the first assumption. For this, I bolded this, samples are independent. We'll get the dependent samples version in a couple of days. Both population standard deviations are unknown, and then you either have that both samples are at least 30 or both distributions are approximately normal. Same assumptions you've had before. The book talks a lot about whether you can assume that the variances are equal or if you shouldn't assume that the variances are equal. And if they are equal, you pool them together, and if they're not equal, then you don't pool. Remember that when we had that with confidence intervals? What did we always do?
No.
Say no to the pooled question. So we are never going to assume that they can be pooled. There's really no advantage to it, so why bother with it? So I put that down here. This is the case we will always use in MA140 at Washburn. Variances are not assumed to be equal. So the only thing you have to understand about that is when you go into the calculator and have to answer the pooled yes or no, say no. We don't do in this class rejection regions based on critical values, but again, they may ask you in the homework to look up a t-critical value, in which case you have to know the degrees of freedom and use your inverse t or click on their table button, but hopefully that won't be the case. So, this simple little formula is the formula for test statistic, for a t-test for two sample means. Does that look at all familiar? Does it look at all ugly? That's pretty ugly. But it really, you've seen all this before. What we're doing is we want to make inference about, we want to compare two population means. We'll call them mu1 and mu2. So I might have a population of males and a population of females. I might have a population of smokers, a population of non-smokers. Whatever it is, I got two populations that I want to compare. And it's the difference between them that is of interest. So we want to estimate that. We estimated it with an interval estimate using confidence intervals. Now we're going to make a conclusion about it using hypothesis tests. So this is sitting right here in this formula. So what is this? It's okay, I can wait. What was the question? This is the population difference. What is this? The sample difference, and it's our estimate of the population difference. So the top of this ugly fraction is the sample estimate minus the hypothesized value. Hey, we've seen that before. Divided by what? What's this thing on the bottom? Standard error. Standard error of this difference. You had this exact same standard error when we did confidence intervals for difference in two means. Right? So it's the same thing that you've seen before, and now we're just forming a standardized score out of it, like a z-score, only we call it t because it's a t-distribution, but that's a z-score. Value minus mean divided by standard error gives you a z-score, a standardized score. So what it gives you back is number of standard errors that the sample difference was from the hypothesized difference. So we're back into that way of thinking about test statistics. Okay, a little bit of discussion about degrees of freedom, but again, the only reason you really need to even understand degrees of freedom here is so you can get through the Hawks homework. They may ask you that. Remember when we did confidence intervals that if we don't pool the two variances, that our standard or our degrees of freedom are the minimum of the two degrees of freedom from the two samples. So you've got sample 1 with N1 degrees of freedom, N1 minus 1. sample 2 within 2 observations, and its degrees of freedom, subtract 1. Whichever one of those two numbers is smaller, that's your degrees of freedom. Enter that into the Hawks. Okay? So, I said before that we use this more complicated formula for degrees of freedom from our calculator. And your calculator, when you do the test in your calculator, it'll say degrees of freedom equal, and it'll tell you some number, and it won't even be an integer. They're using a complicated formula. I don't care if you know that formula or not. If you want to know it, it's in the margin of one of the pages in your book. There you go. But use this if Hawks asks you for the degrees of freedom. All right, let's practice. That was a short lecture, wasn't it? Let's practice. Here we go. Suppose that Smith CPA firm claims that its clients receive larger tax refunds on average than clients of the competitor Jones and Company, located blah, blah, blah. To test this claim, 15 clients from the Smith firm are randomly selected and found to have a mean of 942 and a standard deviation of 103. At the Jones Company, a random sample of 18 clients were surveyed and found to have a mean refund of 898 with a standard deviation of $95. Test the claim made by the Smith firm at the 0.05 level of significance. Assume that both population distributions are approximately normal. Okay? Well, what's the first thing you're supposed to do? Step number 1. Remember, there are 4 steps. What's step number 1? State the null and alternative hypothesis. So let's do that. The null hypothesis, well, remember what we're trying to make inference about. mu1 minus mu2. What would the null hypothesis say that difference is? Okay, now wait, what does the word null mean? None. No difference. So what does the null hypothesis say that mu1 minus mu2 should be? 0. No difference. Right? So mu1 minus mu2 should be 0. Now if we do a one-tailed test, we'll come back and put a less than or greater than above the equal. But the alternative then is mu1 minus mu2 and 0 with a different symbol in there. Now for this particular problem, what symbol am I going to use? What? I don't know, I'm asking you. Would it be? What does the claim say?
They receive a larger tax refund.
They receive larger tax refunds. So it's not a not equal symbol, it's a directional symbol, right? Is larger. Now we have to figure out which direction does it go. Well, you know what? That depends on which one we call 1 and which one we call 2. Which one do you want to call 1? We got Smith and Jones here. Smith, number 1. All right? That's what I would have chosen just based on the order that things come in. The first one they give us is the Smith firm, randomly selected. Then they say the Jones Company, right? So it doesn't matter though. That's the point. Is it's arbitrary which one is 1 and which one is 2. But once you pick a direction of subtraction, you got to make sure you get this pointing in the right direction. So if this, and I do this for my own memory, since I don't really have a memory. I write down which is 1 and which is 2 above there so that I always keep it straight. Now, if their claim is true, Smith gives larger tax refunds than Jones. Smith is larger than Jones. This number should be positive, so greater than 0. Now, it helps to reformat these. This is the way the book does it, and I like this way best also because it goes along with confidence intervals. But as soon as we go to our calculator, it doesn't form it like this, difference equals 0. It forms it mu1 equal mu2. Algebraically, that's the same thing. Add mu2 to both sides, and you get mu1 equal mu2. So algebraically, this is equivalent. Our calculator is set up this way. But it also makes it easier for me when I define 1 and 2 to figure out the directional symbol and then transfer that back over accordingly. But mu1, mu2, if this is Smith, is larger tax refunds would be bigger. Okay? So you'll need to set it up this way when we go to the calculator. But just know algebraically, you move that mu2 over there and it matches. Okay, that's step number 1. What's step number 2? You guys know there's a test coming up, right? Okay, step number 2, according to the book, is, oh, I forgot to scroll down. I forgot to go back. And since this is one tail, I need to go back and do what here?
Change that to a list.
Change it less than or equal. Right? And again, our calculator won't do that. It'll always have an equal there. But. So that's what they have here. Okay? Now, step number 2, the book says step number 2 is to determine which distribution to use, and I say replace that with determine which function on the calculator to use. So look at your calculator, see if you can figure out which function is the right one to use.
The 2 SAMP test.
That's right, 2 SAMP T test. Remember we did 2 SAMP T int when we did confidence intervals, and those two will always be the same first part. If it's the same scenario, means problem, 2 samples, independent, then you'll use the same strategy for confidence intervals and hypothesis test. Just one will say int, one will say test. So 2 SAMP T test. So go ahead and hit enter on that. You push the stat button, then go over to tests, then down to 2 SAMP T test. And it's going to be set up. First thing you have to enter is data or stats. Which do we have? We have stats. They gave us the summary statistics. They didn't give us the individual data points for 18 in one sample and 15 in the other. But they could have. We could have entered those 18 numbers into one list and the 15 numbers into another list, and then we would have selected data. Right? So this is compiling all the information that was in that big, long, nasty paragraph. Right? So when you read those paragraphs, and it just seems like way too much information to process, just start writing down. Every time you come to a number, what is that number? Write it down using the symbols, and it makes it a whole lot easier. Right? So enter these things. I'm just trying to confirm, this is the Smith number, right? So that we did match 1 and 2. Maybe I better go back and check. I think that's right. Yeah, Smith is 942, so there it is. Smith is 942, Jones is 898. So put all those in, then after you get those 6 numbers entered, the next line, actually I should be scrolling down because I think I have this. Yeah, there. Okay. After you get those 6 numbers entered, then you get this line that says mu1 and then a colon, not equal mu2, less than mu2, or greater than mu2. And that's why I say you need it in this form for your calculator. We have mu1 greater than mu2. So select the greater than one. Always say no to the pooled question, and then calculate. So you should get identical numbers to what you see on the screen right now. So remember that big, nasty, ugly formula for the test statistic? There's it is. T equal 1.2656. that's the test statistic. So if you wanted to confirm that, do the calculation by hand, you should match that number. Now, step number 3 is to do this. Step number 3 is to use what you got, what you decided in step 2 to get the test statistic and the p-value. So I'll write that down. Step 3 gave us t equal 1.2656 and p-value equal, what's the p-value? 0.1079 if I go to 4 places. Right? So the calculator doesn't say p-value, it just says p. So p with nothing over it, that's the p-value. Okay? And then it reiterates the degrees of freedom, and it says 28.9. Well, we had 18 and 15. The book would have said, what would the degrees of freedom been for the book? 14. Right? We had sample sizes of 15 and 18. The smallest one's 15. 15 minus 1 would be 14 degrees of freedom. So if you have to enter it, you're going to enter 14 degrees of freedom. Your calculator uses the more appropriate 28.9. It's from that big nasty formula. Okay? So what's the next step? Step number 4. I said there were 4 steps. This is the 4th one, which means we must be ready to interpret what we got and make a conclusion. So, there's 2 parts to that. The first one is, do I reject the null or do I fail to reject the null? And then, we have sufficient evidence or we do not have sufficient evidence. So first of all, reject or fail to reject? I forgot to write it down, but alpha was 0.05, wasn't it? I don't think it's going to matter because this is a pretty big p-value. So, what do we do? The p-value is greater than alpha, so fail to reject the null. So the conclusion, how do you always word that sentence, the conclusion? There is or there is not sufficient evidence for the alternative. So which is it? There is not sufficient evidence. Since we failed to reject the null, you always talk about the alternative in this conclusion statement. And so since we aren't going to reject the null, we cannot support the alternative. So there is not sufficient evidence to conclude. Now, you can't just say conclude the alternative. Right? I want to know it in the context of the problem. So what is the context of this problem? Their tax refunds for the Smith Company are bigger than the tax refunds for the Jones Company. So then you just write all that out. You write what this says, the alternative, in English, in the scenario of the problem. To conclude that the tax refunds for Smith are larger than for Jones. Right? Man, this stuff's easy. Now I want you to go back into your calculator and redo this test. Only when you get down to where it says calculate, instead of pressing calculate, press draw. And it will draw you a picture like the one I'm going to show on the screen. Only mine's prettier. Now if you get an error, some of you are going to raise your hand and go, I got an error. If you get an error, that means you got another plot turned on and it's trying to butt heads with that other plot. So you'll need to go into your plotting functions and turn everything else off to lead them out of there. Anybody have that issue? More than I thought. Press the Y equal button. Do you have an equation in there? If so, delete it. If there's nothing there, then push second function Y equal to get into stat plots
Oh, wait, no, that's right.
and see if any of those are turned on. If they are, turn them off. Okay? Now, did you get a picture that looks kind of like this? So let's talk about it for a second. I'm going to put this up so I can draw on it. This is a picture of the T distribution. Looks a lot like the normal distribution, but remember it's a little more spread out. It's centered at 0 because this is the T distribution for the test statistic. So this number, 1.266, is the number we got for our test statistic. Right? So here's where our data fell, where this vertical line is. This dotted line is where the critical value for T would be. And it's chosen so that this blue shaded area is whatever our significance level is. So in blue is area of 0.05. The fact that our test statistic, if I shade the crosshatch stuff, is the area from where our data fell or more extreme. Remember the definition of p-value? And that's the shaded region, and that's equal to 0.1079. Since the shaded region for our data is bigger than the shaded region for alpha, we fail to reject the null. So all the p-value is, and all alpha is telling me, are you far enough out in the tail to reject the null? Did you get far enough away from the null difference of 0? And here, the answer is no, we didn't really get far enough out. How far would you have to get before you get very excited? For a test statistic. Well, the critical value tells you how far you'd have to go to get excited on a one-tailed test. If it's a two-tailed test, you go about 2. Right? 2 standard errors is starting to get out there in the tails. Since this one's not anywhere near 2, probably not going to reject the null. If you get out to 3 for a test statistic, that's really strong evidence that the null is false because you're too far out in the tail. Okay? All right, let's... before I move on, this is a one-tailed test, so what I'm about to say doesn't apply perfectly, but do a confidence interval for this difference. Instead of a hypothesis test, go back in and do a confidence interval on the same data. But before you do it, predict for me, is that confidence interval going to contain 0 or not? In other words, will the confidence interval lead us to reject the null hypothesis or not? What do you think? Jake, you're shaking your head no. Why not?
Yes.
Well, it's a good guess because you're right. But what made you guess that direction?
I just figured since we're pretty close to the standard deviation away, that it's not going to be 2.
Okay. That's right. This is in pretty close, so a confidence interval is going to overlap 0. Right? And you can tell without any doubt based on the p-value. If the hypothesis test fails to reject the null, then the confidence interval must also fail to reject the null. Those two will always make the same conclusion. Now, what I said a minute ago, for a one-tailed test, and by definition confidence intervals are two-tailed, then if I use a 95% confidence interval, then that's a two-tailed test. They won't match up exactly. In this case, I think it'll still be all right. But to make them match, you make the alphas. If I were doing a two-tailed test, I would be doing alpha equal 0.025. Right? No, I'm sorry, I would double it. I'd be doing a 0.10. So I'd have alpha 0.5 here and another alpha 0.5 here. So if you do a 90% interval, then you'll make the same conclusion that you'll make for a one-tailed 0.5. Right? So do a 90% confidence interval. How do you do it?
No, just like back so you
Oh, it should still be in your calculator. Right? So to do the test, you're going to do 2 samp t int. I said to do the test. To do the interval, you're going to do 1 samp t int instead of 1 samp t test. And all the last thing you entered is probably still there. Or does yours zero it out?
Yeah.
Oh, okay. Some calculators do that. They default every time you do a new thing, it zeroes it back out. So here's the data. And when you get your interval, tell me what it is. We've already decided that interval is going to contain 0. Since we failed to reject the null, we know that 0 should be possible. You got it, Jake?
Yeah, it's negative 15.08 to 103.
103?
Yeah, 103.
Wow.
Which one is it?
I'm wowing because 2 reasons. That's really wide confidence interval. But the sample sizes are pretty small. Standard deviations were pretty big. But what'd you say?
What function are you
2 samp t int. But it does contain 0. But it actually barely contains 0. 0 is close to the boundary, right? Well, remember that our test statistic was actually pretty close to the critical value. So since it was close, our confidence interval is going to be close, but still contain the null hypothesis. So you can always do a hypothesis test using a confidence interval instead of a p-value. I like confidence intervals better because they give you more information. They give you everything that the p-value gives you, which is essentially reject or not reject. But they also tell you, well, how much spread is there in your precision of your estimate? Where is the difference? The difference is somewhere between negative 15 and positive 103. So what would you do if you worked for the Smith Company? You just failed to reject. You can't make your claim based on this data. What would you do? No, you wouldn't lie? That's for the statistician to do.
Right.
But what could you do? What'd you say?
Skew the data.
Make the confidence interval smaller.
Make the confidence interval narrow. How do I do that?
Like lessening the percentage.
Okay, I could change this, but then people see through that. Oh, you're only 80% confident? Right?
Smaller.
What else can I do to make it smaller? Increase the sample size. They only took 15 and 18. So I'd compute this, I'd say, hey, you need to go get some more data. So they get another 15 and another 15 on the other side or whatever. They double their sample size. This shrinks, and all of a sudden it doesn't include 0 anymore. Now that's making the assumption that the means stay where they were. But if they're good estimates and random samples, they probably will stay close. So this is really probably a type 2 error. Since it's almost rejecting the null, but not quite, then you say, well, you just didn't have a big enough sample size. And that's why it's worded this way. There is not sufficient evidence. You had evidence from 15 and 18 clients. That's not sufficient. Get evidence from 30 clients on each, and you'll probably be fine. All right? Okay, let's do another example. From our class data, we took observations of resting pulse, and then we asked a couple of categorical questions. Do you exercise? And do you smoke? So have you heard that regular exercise reduces a person's resting pulse? Have you ever heard this? You've heard it from me, I know, right? Well, let's test that claim. Using our class data, let's test this claim using a significance level of 0.05. All right? So I want you to do this. Step number 1, state the null and alternative hypothesis. I know you're used to a lot longer paragraph than this, but let me show you the data. It says that the important sentence here is regular exercise reduces heart rate. So here's the data. All right, so I've got non-exercisers and then exercisers. So if I call this sample 1 and this sample 2, put this up where I can write on it. Call this sample 1 and this sample 2. Form your null and alternative hypotheses. And you go ahead and do it, and then we'll work it together once you get done.
Do you want to go back one slide for
What did you need off the other slide?
a second?
Alpha?
No, like it, I just put one into it.
Right? So test the claim using significance of 0.05. Exercise reduces heart rate. Write your null and alternative hypotheses first. And make sure you can get that right. Yep. No, you do want 0. The difference is either 0 or it's not 0. But then you got to get your direction in the right direction. Direction in the right direction.
Put mu down, given E up.
We never put sample data in our hypothesis. Right? We don't have to make inference about sample data. We can look at that. So, I'm saying, do it just like the one that was over there, but in your notes, it was just like this, with the symbols like this. Right? Okay, you need a mu1 and a mu2. E's, which are proportions. Yep. So, you got your okay? Good. Actually, let's see, direction. You have less than this. But if the bottom row is exercise, then exercise should be. Oh, this is exercise, this is not exercise. When I take the difference, should I do positive or negative? One is not exercise, the other way.
Okay.
No, it was $160 just to
Good.
fix the screen, so I was like, I might as well order it as one.
Getting confused with that mu and that 0.
Now, it helps me. I see a lot of you struggling with the direction symbol here, right? The book will do this, mu1 minus mu2 and 0. That's always going to be the case for these two independent sample problems. You're going to have mu1, mu2, difference, and a 0. And then you're just figuring out the symbol, right? But it's easier, I think, to first write it the way your calculator wants it. And your calculator wants null hypothesis, mu1 equal, the null is always equal, mu1 equal mu2, and the alternative mu1 and mu2 with some symbol in there. Now, if the claim is correct, and exercise, this is yes for exercise and no for exercise, if it's yes, and I call this mu1 and yes mu2, then which should be bigger?
U1 should be, have a higher heart rate.
Mu1 should be bigger than mu2. And notice the data is going in that direction. But if exercise reduces heart rate, then the exercise mean should be less than the non-exercise mean. But we've got them non-exercise, so non and exercise. So non should be bigger. Now if I subtract mu from both sides, I'm in this form, I'm going to use the same symbol. There are a sufficient number of people on the next test that will miss points because they get that going the wrong way. All right? Now, well, I'll come back. Remind me to come back and show you what would happen to your p-value if you point it the wrong way, so that when you see it, you'll go, oh, I must have done that one mistake. Okay? So there's your null and alternative hypothesis. Now, the second step is to decide what thing to use on your calculator. We've already done that. It's all in the same section, 2sampt int. But then third step is to do it. So go to your calculator, enter the values, and the 6 numbers you need are right here. Right? They're not in the same order your calculator's asking, but the mean is x bar, ends, and then standard deviations are your s's. So this is, for sample 1, I'm going to read them for the video. 147 for sample size, n, 75.33 for x bar 1, and 11.79 for S1. Then sample 2 has an N of 218. An X bar 2 is 70.4, and S2 is 12.54. Are you keeping what? I couldn't hear you. No, we're doing a test. Your hypothesis test. People getting answers?
3.818.
3.818. Before you do anything else, look at that test statistic. What did we say a minute ago? It gets how big before you start to get excited? If it gets about 2, that's getting out there. This is almost 4. So what does that tell you about your p-value?
It's really small.
It's going to be really small. But it's one of those tricky p-values. It says p is equal to what?
8.037.
8.037.
-5.
And then if you don't notice the e minus 5 out there, you write this down for your p-value, and somebody will do this on the test. They'll write this down, and then they'll look, oh, what's my alpha? 0.05. Well, this is bigger than 0.05, so I do not have sufficient evidence. But if you understand what a test statistic is, you should already know, ooh, I'm going to reject the null. I'm way out in the tail. So my p-value should be really, really small. You'll catch that mistake and go, oh, wait, there's an e minus 5 out there. So that p-value could be written as 0.0000804 by round. So now, what's the conclusion? We're going to reject the null, because this is way less than alpha. I don't remember, alpha was 0.05, right? So it doesn't really matter what alpha was, we're going to be less than n. So the conclusion is, there is sufficient evidence to support the claim that regular exercise reduces heart rate. Okay? Any questions on that? Does everybody understand it? All right, let's do one more. Okay, question?
Could you just explain the alternative again?
This one?
Yeah.
The alternative is a greater than 0. First of all, it's a one-tailed test because the way the sentence was worded. Remember what it said? Test the claim that exercise reduces heart rate. And the key word is reduces. That's a directional word. You know, sometimes they'll say less than, sometimes more than, sometimes at least this, or whatever. But any word that implies a direction. Right? So that's why it's a one-tailed test. And then you just figure out, oh, well, which one am I calling sample 1? Which one am I calling sample 2? And then figure out, well, which direction would it be if the claim is true. If it does reduce, if exercise reduces, then mu2 should be less than mu1, so it goes in this direction. And then I can apply that same direction here. Right? What about smoking? Does smoking affect heart rate? What do you think? Do you think it has as big effect as exercise? You say bigger? Some people are saying smaller. Yeah. Let's find out. Okay, so we'll do the same thing. Look at that, my screen didn't quite match up. Let's call sample 1 the no's. This is to the smoking question. So no and yes for sample 1 and sample 2. And I'll make these numbers a little bit bigger so I don't have to read them. But before you go to your calculator, do the eyeball test. That's a 9. Look at the numbers. Does it look like there's a difference? Does it look like it's a statistically significant difference? Yes. But be a little bit careful, because this idea of statistically significant has to do with how variable things are, right? All about width of confidence interval, and what our sample sizes are. Well, the sample size in the yes group is getting pretty small, 39. The other one's huge, no problem. But our standard error might be a little bigger now than it was before because of this small sample size in one of the two samples. Right? But still, that's an 8 beat per minute difference in heart rate. That's even bigger than what we saw with exercise. So go ahead and conduct that hypothesis test all the way through, just like we did a minute ago, and make a conclusion. And I'm going to come around and look at your hypotheses. I'm going to look at your test statistic, and I'm going to look at your conclusion.
What's the standard deviation for sample
11.87. Yeah. I got it on that little bar, and it's hard to read. If you get stumped, you're not sure where to go next, instead of just staring blankly, raise your hand. I'll come around and help you. I was going to walk down this aisle, but I want you guys to make this. No, you don't have to move stuff. I'm athletic. Yeah, keeps you away from, keeps me away from it.
The last one I still think is 0.05. Is that correct? What's alpha in this problem?
Let's do alpha equal 0.01 this time. Yeah. So use alpha equal 0.01. And again, I don't know that that's going to matter a whole lot.
did something.
You don't need alpha.
I just.
So then why, what, why am I doing this?
Because that's how you compare the p-values. What's the keyword?
I'm kidding.
Yeah, I got you. Did you catch that? Nope. That symbol is not going
This one, right?
No. What does it say up there? Read the sentence. Is resting heart rate different, which does not specify direction, so then it's a not equal. I intentionally didn't say that before I cut you guys loose. Okay, good. Oh, I just noticed that the time has expired. So, let me sum up real quick and then I'll let you go. The hypotheses, it says different, so you need a not equal symbol. It's a two-tailed test this time instead of a one-tailed test, right? And then you got a test statistic again in the threes. I don't remember if it was positive or negative, but negative 3.28, wasn't it? Okay, and then p-value of 0.00222. So again, very small p-value. We're going to reject the null hypothesis. There is sufficient evidence that smoking heart rate is different than non-smoking heart rate.
I don't suppose a t-value of 2008
No, there's something probably wrong with that. So we'll see you on Friday.